Put that in my pocket.
Okay, you're live up on the screen, you're live on live stream.
Wow.
People should be able to hear you.
Cool. We have technology. Oh, that's cool. My forward and backward buttons aren't working. There we go. Let's try that. Okay. So hey everybody, my name is Reid Wightman. I currently work as a vulnerability analyst at a company called Dragos. We do mostly critical infrastructure protection, so a lot of industrial control systems, electric utilities, that sort of thing. Today I'm going to be talking about a little research project I did a while ago. This is actually like 2 or 3 years old at this point, but still pretty cool stuff and actually really relevant. So the talk is called Network Switch Inception, which is basically like we're looking at network switches and seeing what we can do once we root a network switch. So this is not actually a talk about network switch vulnerabilities. The kind of impetus or the way I got started on this whole subject were a bunch of colleagues of mine, this Rob Lee, who's now my boss technically, Aaron Leverett, who is a really awesome researcher that I used to work with, and a bunch of other guys, Colin Cassidy and a few other people, did a series of talks called Switches Get Stitches, where they were basically like looking at industrial network switches and taking a look at what vulnerabilities were in those network switches and how to exploit them and like what was wrong with them. And it was kind of interesting because those switches they were looking at were focused on industrial. So they were industrial hardened switches meant for harsh environments. So they were the sorts of things that would be installed in generator plants, substations, that sort of thing. The reason I kind of dusted off this talk and started looking at this research again was this DHS advisory that came out recently, this TA 18106 advisory, where they actually named Russia as a state sponsor of a whole bunch of people that are going after network infrastructure. So there are a bunch of attackers, targeting specifically network switches, network routers, VPN gateways, that sort of thing. There were, and over the years, actually, there have been a whole bunch of vulnerabilities, both in Cisco gear and Juniper gear. In fact, I think 2 days ago, there was a disclosed backdoor account in Cisco's network management system for managing Cisco network switches that was self-disclosed by them. Kudos on them. But, clearly, there are a lot of vulnerabilities in this stuff, and actually, there are bad people that are actually going after it. So it's cool to kind of look at, just how bad it can be if somebody happens to exploit one of these systems. So this is really a talk about post-exploitation, right? So this is like, say we have a layer 2 managed network switch, just some ho-hum network switch, or of course it could be something more sophisticated, but we hack the switch, but as an attacker, what can you really do when you break into a network switch? So the victim switch is this 6-net industrial Ethernet switch. I bought it specifically because of the little penguin. Because the network switch is a managed network switch, and it actually runs Linux under the hood. It's the sole reason I bought it. I thought, hey, this could be kind of cool for a little research project. Inside of the device, there is a little ARM9 CPU, this little Atmel chip. Up here, it actually has a lot of flash memory, and a lot of it's free. It has 128 megabits of flash. That's what, 16 megabytes. I think about half of it was used by the actual firmware. It means you have tons of room to load your own tools onto it. And then it has this Marvel 88E6083, what they call the Easy Street chip. It's a network switch chip that's inside. It also has some SRAM. I forgot to take pictures of the SRAM. I think it's got 8 or 16 megs of RAM. I can't even remember. The actual exploit, again, this isn't a talk about exploitation, but the exploit that I used was a directory traversal bug. If you back up the configuration of the network switch, the backup is actually a tarball. So you download a tar.gz file. The tar.gz file actually has like the /etc directory in it. So I did a couple of little tricks. One of them was putting a symbolic link to the etc password file so I could retrieve the etc password file from the web directory, and then inserted my own etc password file, preserving the existing accounts and adding a new account so that I could actually have a root shell on the device. But this is really a talk about post-exploitation, right? So we've got admin on the switch. We actually have a root account where we can log into the switch via telnet or SSH. Now what do? There's a bunch of boring attacks we can do to start with, right? One is to disable network interfaces. You can obviously, if you have admin on a switch, you can turn network ports on and off. You could disable the network mirror port. That would, blind an IDS or IPS or whatever you happen to be running on your system. You could also lock the administrators out. You could change their password on them, or you could just entirely disable the management services, SSH or the web server. The official story, though, is that it's a layer 2 network switch, right? It's pretty limited in functionality. Aside from doing one of these like really obvious attacks, it doesn't seem on its surface like you could do too much very interesting. Really the switch chip, that Marvel chip inside, its whole goal is it just receives a packet on one port, says which port has the destination MAC address of this packet, and then puts the packet on the appropriate port, right? Doesn't really have any advanced features, except that actually it does. So we need to look a little bit deeper at what the network switch chip can do and how to use it. So network switch chips, and in fact all network components, are configured by this little protocol called MDIO. I forget what it even stands for. It's like multi-data in-out. It doesn't really matter. It's a serial protocol used for reading and writing configuration registers on the chip. There's not much that we have to worry about for the purposes of this talk. We don't have to worry about the ins and outs of the protocol because the operating system that's already loaded on the switch will take care of that for us. But again, there's that kind of theory or idea that these network switch chips are just things that handle packet matching. But they're really highly configurable, and there are two features common to all network switch chips that will be the downfall of a network switch that will make it really interesting. That's VLAN tagging and port mirroring. And in fact, a lot of modern switch chips, including this Marvel one, actually support layer 3 in routing. Like, most of these switch chips are meant not just for use in switches, but they're meant for use in either a switch or a router, depending on how you configure the switch using those configuration registers. So this is the switch chip, the architecture diagram of the switch chip in the ET-9MS. This is a switch that has 9 Ethernet ports on it. So a pop quiz is, how many Ethernet ports are actually on the switch chip, the Marvel chip that's inside of the switch, right? Can we count? So it's pretty small to see, but there's actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's a 9-port switch, but it has 10 ports. Everybody asks, why are there 10 ports? And it's actually a dirty secret of all managed network switches, right? You actually have a processor inside of the network switch. That processor has to be connected to the network so you can connect to the management services, the web application, the SSH server, that sort of thing. So rather than having to plug a loop-back Ethernet cable from the network switch to the CPU inside, they just use that extra port to connect the processor directly to the switch chip. But a side effect of that is that the CPU can actually reconfigure the whole switch chip, and it can also eavesdrop on traffic, and we'll see how to do that. The functionality, that functionality is always hidden by the firmware, but we're root now, right? We own the firmware, so we can do what we want. So now we have the ability to do this whole thing where we eavesdrop on traffic and reconfigure the switch chip on the fly, so we can do all kinds of crazy things now. So it turns out layer 2 switches can all become routers, right? Who knew? The first thing we need to do is to figure out, which of the ports on the case, those 9 Ethernet ports that are exposed on the case, connect to which ports on the switching fabric. That way we can figure out which port on the switching fabric is actually connected to the processor. There's really 2 methods for doing that. One is continuity testing. It means you actually open the case, you trace out the little data lines and check, hey, this pin on the switch chip connects to this pin on the processor, so that is the port. If we're lazy like me, we've rooted the switch, we can just start poking around and looking for configuration files. And it turns out on this switch, there's a configuration file, etc switch swm.config. It has the whole mapping spelled out for us. And it actually tells us that case port 0, which is not actually a physical port, connects to port 9 on the switch chip, which is the hidden port that is not exposed to anybody except us now because we're root. Next, we need to learn how to actually interface with the switch chip, using that MDIO protocol. I said we wouldn't have to worry about the low-level details of MDIO, and we don't. We find this library called libswm. It's in user lib or whatever on the network switch. We want to build our own application to use this library for actually interacting with the switch chip. And we need to actually build our own headers. to actually interface with this library, because shared libraries on Linux systems don't include some key information. We'll walk through how to do that. Then, obviously we need a cross-build environment where we can actually compile some code that will link to this shared library and use the functions in this shared library to do what we want. So to compile our own code, we need this header file. So this libswm library that we're looking at, there's no published or documented anything about this anywhere. The company had originally promised to publish an SDK for their network switch, probably so you could do some crazy advanced features in the industrial space, like monitor network traffic on the switch or do some kind of internal IDS or who knows. But they never actually published it, so we need to kind of figure it out. The kind of way that we're going to do that is looking at the combination of assembler code and kind of bumbling around with some C code. So we load up that libswm into our favorite disassembler and find a bunch of interesting function names. I mean, first off, I should say that the library has debugging symbols, so we actually get function names as part of the library. But we don't get what parameters are passed to that function, right? We just get, hey, this is a function called register dump. It takes some argument, and we have no idea what those arguments are, right? So we need to figure out what the arguments are. So, we're going to start figuring that out. So that we know that register dump function that we saw back here takes one argument, and it looks like it starts printing out the registers from the switch chip itself. Apparently, it takes some kind of data structure as an argument, and it looks kind of like an MII bus struct, which is this Linux kernel data structure. So we actually allocated one, wrote some code up, tried to use it, programs always crashed. It turns out there's this other function in this thing called findSWM, and it returns a big data structure. We have no idea what it is. I'm like, maybe it's the same thing. So let's try it and find out. So we write a little stub C program that calls the findSWM, basically voids out the result saying it's a void pointer, calls that findSWM, passes it to register dump, and then calls register dump with that result of findSWM as an argument. And sure enough, it starts printing out global registers, and it doesn't crash, and everything looks great because the global registers that it prints out kind of line up with what we see in a data sheet as what we expect the switch to be configured like. So there are two other functions inside of the libswm library, mdio read and mdio write. They're the only two functions that we actually need to achieve all of our goals, because these are things that let us read and write those two register values, or they let us read and write all the register values on the switch, but they're what we need. So we look to the data sheet and we see, okay, there's this particular register here for controlling ports, and one of the bits inside of that configures whether or not the mirror port source is this port. So we start to get an idea for what this looks like. So they're all we need. They allow us to read and write any of the configuration things we need to know, and we basically know enough to start doing some interesting stuff. So we want to accomplish two goals as an attacker, because I'm, former bad guy. Well, not really former bad guy, but sort of former bad guy, at least devious thinker. I kind of wanted to look at whether we could pull off a couple of neat tricks. One of them was to do a fake mirror. That is, can we take a mirror port and hide traffic from it? That way we could, for example, if we have an operation going on, and we want to hide the operation from an intrusion detection system, can we make most of the traffic go to the IDS, but hide the malicious traffic? So, that's one goal. Another goal is, can we do packet filtering? That is, let's say, I'm actually following a protocol stream. Can I actually edit packets in the protocol stream on a network switch? Manipulate traffic at the application layer, actually overwrite requests or overwrite results. And we want to do this in a way that avoids any of these chipisms. Like I said, this Easy Street chip actually has some crazy advanced features. It's meant to be used as a router, but I kind of want to avoid that. I want to make almost a framework that's more generic that can be used to attack basically anybody's switch, whether it's this 6net thing or a Cisco switch or any manufacturer's switch. So the way normal mirroring works, right, is you usually have a bunch of ports, at least one port, maybe a bunch of ports connected to some devices out in the field. I'm an industrial control systems guy, so usually what I see are PLCs, programmable logic controllers. But you could just think of this as any computer. And then you have, some network port that connects upstream to the larger network. So you generally take that upstream port and mirror its traffic to a mirror port, connect that mirror port up to an IDS. Yeah. So, we want to find, first off, if we want to pull off this attack, we want to find the port that the user is actually mirroring the data to. We want to redirect that port to the chip's onboard microcontroller, its onboard processor. No longer mirror it to the IDS, instead mirror it to the processor on the chip. Use the chip's processor to sniff the traffic, decide whether an incoming packet is interesting. That is, should the IDS actually see it or should the IDS not see it? If we're supposed to mirror it, we would actually temporarily re-enable mirroring using the chip's port, like the switch's internal port as the source, with the original destination as the destination port, retransmit the packet, and then we would disable the mirror port again. It's kind of lame, but it works. So, kind of in pictures, how this works is we redirect that, upstream mirror port over to the CPU. Once we see a packet, we decide whether it should be seen. If it should be seen by the IDS, we retransmit it. If it shouldn't be seen by the IPS, we just, we ignore it. Hey, it's got this special MAC address. The IDS doesn't need to see this. It turns out there's not a whole lot of extra code needed to pull off this attack either. So the 6-net switch actually included libpcap as part of its firmware. So we were able to, use that. And I should mention, I've heard Nick Stark, if you guys haven't heard him speak here before, he gives a lot of cool talks on Internet of Things, reverse engineering, and hacking. One of the banes of our existence when you go into writing your own code for an embedded system like this is the whole cross-compiler. It turns out in this case, getting the cross-compiler to work was really easy because the whole libc, glibc, and all these other libraries were compiled and they had a little signature in them saying I was compiled with this cross-compiler called ELDK 4.1. It turns out you Google that, it's like a German cross-compiler vendor. You can download RPMs of their cross-compiler and install them inside of, I think I installed it in Fedora Core 7 or something and got it working and was able to cross-compile and link all my applications to these libraries, no problem. But the fake mirror library that does all that logic where it actually will monitor the traffic and decide whether or not to remirror it, and this is based on a MAC address. The total compiled size is under 12 kilobytes, so it's not a whole lot of code. Couple of problems with this whole attack. First off is duplicate packets. The real target of the packet that's supposed to be seeing the packet will actually see duplicate packets because we're resending the packet with the mirror enabled and the CPU's internal or the switch's internal CPU port as the source. So the destination will see multiple packets. It's actually not a big deal. Most operating systems really don't care. They're just like, oh, it's a retransmit, whatever. Problem 2 is latency. If you were really, really paranoid, you could watch for this, and you might even be able to detect it. As far as I know, no intrusion detection system can actually do this yet. I actually asked the Bro guys about this a couple of years ago, and they were like, yeah, we wouldn't be able to do anything with just a few milliseconds of jitter. So normally, while this is just doing some basic attacks, just TCP connects and that sort of thing, normally we see on this network switch 0.6 to 1.2 milliseconds of latency, round trip between a packet going out and a packet coming back. While we're doing this attack, we see usually around 5 milliseconds if we're paying attention on our IDS. But again, there's no intrusion detection system language for expressing normal packet delay or packet jitter at this point. Maybe Bro has it now, I don't know, but at least at the time there was no way to do it. The other real problem, though, is mirroring the administrator traffic. So if you're doing this attack and an administrator happens to log into the switch, depending on the configuration of the mirroring and the IDS, it's possible that the IDS will see admin login traffic that it shouldn't see. In that case, probably the gig is up unless your sysadmin is asleep at the wheel or something. So I'm not going to release the code for doing the Leverett attack publicly, but I did put a bunch of code up on GitHub for at least letting you explore. If you happen to buy one of these switches, you can start exploring the whole MDIO protocol on the switch. If you feel really empowered, maybe you could rewrite it. It really isn't that hard. But this does do really reliable IDS evasion. So if somebody roots one of these switches and you're relying on the network switch mirror for IDS, you kind of lose. And kind of a bonus from the way we do this, where we actually have root on the switch and are editing the configuration directly, is all the switch configuration GUI stuff, like the web interface and stuff. The web interface actually reads from those config files to show you how the switch is currently configured. It doesn't bother querying the switch chip again. So, doing this where you have root on the switch, you actually get stealth for free. So you don't have to worry about trying to hide the attack from the GUI anyway. So the next attack we'll look at, that was one. That was kind of the IDS evasion, port mirroring, fake port mirroring attack. The other attack we'll look at is one where we can actually manipulate network traffic. So like I said, hiding from that mirror thing is fun, but can we really manipulate traffic? I mean, there's a really obvious way you could do it, which was to use ARP poisoning, right? You could actually use the processor inside the switch to do ARP poisoning on the switch. I don't like that because it's really noisy, and everybody does ARP poison detection, right? Does everybody do ARP poison detection on their network? No? Okay. I didn't think so. Nobody does. But still, we want to be more stealthy. So there are a lot of ways to pull this off. The most generic way that we found was to use that mirror port thing again, where we would mirror two ports this time. Say we have computer A connected to port A, computer B connected to port B. We'll just mirror both to the microcontroller inside of the switch. And then we can use VLAN tagging to kind of force the routing to go through that inside processor. So basically, if we put system A and system B on separate VLANs, we can use the mirror port function so that the processor inside is always seeing the traffic, and target A and target B can't talk to each other directly. And then we'll just manipulate mirroring to take the packet, edit the packet, and then transmit the packet to the appropriate destination. So how that looks is, we have port A, or we have system 1 and system 2. We put them on VLAN 1 and VLAN 2. We have the port mirroring set up so that the CPU sees a mirrored packet coming from system 1, decides the CPU will actually modify the packet, and then it will transmit it to system 2 using probably like a spoofed source MAC address or something like that. So, it's easy peasy, and I would say consider it a really simple attack, right? If somebody pwned your network switch, they could use this to really easily manipulate DNS traffic, right? It would be super easy to parse DNS queries, overwrite their responses, point people on your internal network to a malicious server, and it could have some really bad results. In the industrial space, we have all of these protocols that are insecure by design. We have all these protocols like Modbus and DNP3 that have no authentication, no encryption, no nothing. So using this kind of attack against those is also kind of a no-brainer. Wouldn't involve anything super crazy. Of course, if the connection happens to be encrypted or whatever, then that would suck. We wouldn't actually be able to manipulate the traffic, but for a lot of stuff we can. So who's vulnerable to all this stuff? Pretty much any network switch that doesn't do firmware signing, which is pretty much every network switch. And even network switches that do firmware signing, pay attention to how they sign their firmware. Vendors love to sign firmware updates. That is, like, you download an update. When you apply it to the network switch, the switch is verifying the signature of the updated firmware, but then there's no subsequent verification of the firmware ever again. So if the switch is rebooted, there's no actual check of a signature of the firmware at boot time. It basically means any vulnerability in the network switch, anytime ever, could result in compromise of the firmware, which means that somebody could do the nasty stuff to their firmware. But basically any network switch, to summarize, I guess it would be any network switch with this hidden CPU interface, which again is basically any basically managed network switch. Essentially, if you can plug the network switch into your network and then visit some kind of a web server or SSH server on the network switch, probably it's going to be vulnerable. So it turns out these layer 2 switches, I guess kind of takeaways are these layer 2 switches can be at least as important as routers for data integrity, right? They really can be turned into cool attack platforms. Switch rootkits probably already exist. I think when I was originally giving this talk, it was a hypothetical, but I think since that time, we've seen some leaks from the government or whatever where there are actually like switch rootkits out there, and I'm sure that the U.S. are not the only ones that have such things. And really rarely are these things patched, right? I've been talking to some folks that have Cisco switches, and they're like, oh yeah, we have this thing, it's 5 years old, we haven't paid the support contract or the maintenance contract on it, so we can't even download firmware updates for the thing. So it's got a whole bunch of vulnerabilities in it that will never get fixed. And it's actually impossible to audit most of these network switches. There's no mechanism to do it. The only way to really properly audit most embedded devices is to open them up and start desoldering stuff, and then you're never going to put it back into a production. So it's, I don't know what you call it, like Schrodinger's firmware or whatever. Anyway, mitigations. Really what you want to do if you have managed network anything, put them on some kind of network management LAN. Don't leave these things manageable from your corporate network especially. Remember, people on your corporate network are getting spearphished every day. If you're managing your network infrastructure from the corporate network that's probably compromised, you're probably in trouble. Disable management interfaces that are corporate facing, either use a dedicated network management LAN or, if you're an industrial control systems person, put the management interfaces on your ICS network. And really monitor the traffic to those network switch interfaces, right? There have been a lot of guidance put out in that DHS advisory, just mentioning ports to monitor. A lot of it pertains to the Cisco stuff. There's that whole Cisco Smart Install fiasco that's probably never going to die, where if you upgrade the firmware in Cisco switches, it automatically automatically enables this Cisco Smart Install feature that allows remote administration of your network switch with no authentication. It's pretty cool. But just monitor your network for traffic either to that port or to any of the normal network switch management ports. And that's all I've got. Questions?
Could you automate a script to go through all your switches to do like validate or verify the iOS image validity, make sure the hash is changed?
Yes and no. I think that you could, but again, I think if your network switch was actually compromised and the attacker had adminned your switch, they could just hook the print out the hash of the firmware function, right? To be like, oh, I know what the hash should be. I'll just give the guy that and let him run to town. Kind of comes back to the whole firmware attestation issue. Sorry, it's bad news. Any others? Okay, well, if anybody has questions, I'll be around. You can always email me at work or catch me on the Twitters. Thanks. Oh, right on.
So Britney Spears. I hate that thing. Sweet. All right. So as what we always do with our first-time speakers, we always have a quick gift for them. So we got a shirt and a patch for our first-time speaker, Reid. Thank you very much for presenting. It's awesome. Thank you very much.
Sorry, I got your table.
Oh, was it mine? Oh. We also do have a CTF winner as well. So we'll take a quick break for a little bit, and then we'll have the CTF winner come over and kind of present on how they were able to solve that challenge. So maybe give it a